Up to now, when we've been talking about stresses and beams and bending, we've always been talking about the bending stress, so which is the normal stress in the x direction, which varies as a function of y. But hopefully you've noticed that there should be shear stresses in these problems, and we really haven't said anything about how one computes shear stresses. So let's go ahead and consider that issue now. So if I have, for instance, a cantilever beam with an end force P on it, there's definitely going to be shear stresses in the system because I have shear forces, and we know that the shear forces in the y direction on any cross-section of the beam are going to be equal to the integral of the shear stresses, the sigma xy's in the beam. So we should have an ability to calculate the shear stresses. So if I look at a section cut anywhere along the beam, I have Vy is equal to P, and that means that I'm going to have some sigma xy in this system, and I'd like to be able to calculate what that is. Now, one of the things that complicates this is the fact that our kinematic assumption for the behavior of beams tells us that the shear stresses gamma xy are equal to 0. So the normals remain normal assumption in the beam is telling us that the shear strains are equal to 0, and by the elastic relationships that means that through the constitutive law that if I multiply by the shear modulus G, I should get 0 for the shear stresses. But that seems to be in contradiction to the fact that I actually have shear forces, because recall that the shear force in the beam, so the let's say the shear force in the y direction is equal to the integral over the cross-sectional area of sigma xy dA. And so if sigma xy is equal to 0, how is it possible that Vy is going to be non-zero in this case? So the way to think about this, or one way to think about this, is that if you want to have zero shear strain in a system, you need either that the stress is equal to 0, sigma xy is 0, or that the shear modulus is equal to infinity. So it seems a little peculiar, but if you want to have no shear deformation in the system, one way of thinking about that is that you have an infinite shear modulus in the system. And if you have an infinite shear modulus in a system, then you have the situation where you can have 0 shear strain multiplied by an infinite modulus and still get a finite value for the shear stress. And that's really what's going on here, and it's kind of a peculiar fact of the assumptions that we've made that we have no shear deformation, and that forces us into this odd situation where we have 0 times infinity giving us a finite number. Okay, and so we'd like to kind of see what we can do in terms of at least getting some kind of estimate of what sigma xy is in the beam, even though we've forced ourselves into this odd position because of our kinematic assumption that there are no shear strains in the system. So the basic problem again is that gamma xy is equal to 0 by assumption, but in reality there's always going to be some gamma xy. So the 90-degree angle that we have, normals remain normal, is really not quite true. There is a little bit of shear deformation which produces a little bit of shear stress, but we really don't have a way of getting around that directly because the fundamental assumption involves the shear strain being exactly equal to 0. Now, one thing that we could do is just to say, well, I'm going to work with average values. Let me go ahead and divide the shear force V by the cross-sectional area, and that will give me sigma xy average on the cross-section, and then I could back calculate an average shear strain on the cross-section, which would be V divided by GA. So that's one solution for getting an estimate on what the real shear strain and the real shear stress is inside a beam with a transverse load on it. But it turns out that we can actually do a little bit better than just average values. We can actually get point-wise values or on the cross-section and how they change from point to point. And the way we do that is we can kind of use an equilibrium model. So remember that if I have a rate of change of the moment, so dm dx, that means that the shear force is non-zero. So anytime I have a shear force, meaning I have a shear stress, I'm going to have some rate of change of the moment along the length of the beam in the x direction. And this actually allows me to produce an argument that will allow me to determine what the shear stresses are in a better way than just computing the averages by taking the force and dividing by the area. So let's consider a beam, and I have the x-axis along the length of the beam, the y-axis in the vertical direction, and I have a non-zero shear force in it. And if I do that, and I look at a little section dx, and I draw in the stresses, so the bending stresses. I have, say, on the left side, I'll have minus my over I, so I've made a section cut at some distance x from the end of the beam. And then on the right side, I'll have a bending stress distribution, which looks a little bit different than the distribution on the left side, because the moment on this side is going to be different from the moment on the left. So I have a moment on the left, which is m evaluated x, and the moment on the right is m evaluated x plus delta x. And so the stress distribution on the right side is minus this new moment times y divided by I. And the values are going to be a little different if the shear force is not equal to 0. So what I have here is a model of what we've just talked about, and what I have is I've taken a section cut out of an I-beam, and this is delta x, and the beam is subjected to some moments and shears. And so I have a moment on one side here on this section cut, so I have the stresses from the moment on one side, and here on the other side I have the stresses from the moment on the other side. And so to get to the shears, what I'm going to do is I'm going to make a section cut, a horizontal section cut in my differential element. So if I do that, I have stresses on both sides for my moments, and those stresses are different from each other. So let me go ahead and subtract off the same amount of moment and the resultant stress from both sides. So if I go ahead and do that on my beam, you'll see I have some stress that's due to the differential moment from one cross section to the other. And to keep the system in horizontal equilibrium, so equilibrium in the x direction, our usual coordinate system, I'm going to need a force here to resist that. And if there's a force on this surface here, I can divide by this area here, and I'll have the shear stress on this surface here. Now, if I have the stresses on this surface, I can use our understanding about moment equilibrium in terms of stresses. That tells me what the stress on the orthogonal surface is. They have to be equal to each other. So now I have a stress on this surface here. Okay, so let's consider the little setup there that I have more analytically. So let's consider a section of the beam of width delta x. We'll go ahead and make this rectangular, so we'll have height h and width b, and we'll put a coordinate frame right in the centroid of the cross section, so x, y, z. And let me go ahead and consider a horizontal cutting plane, so whose height above the z-axis is going to be y1. So we're going to chop off the beam at y1. We'll try and compute the forces on this cutting plane, and then the shears on that cutting plane, and then we'll transfer them to the vertical YZ plane to give us our sigma XY values in this system. So that's going to be the goal here. So if I draw the system from the side, I'll put the moments in, or the bending stresses from the two moments. So I have the moment on one side being greater than the moment on the other side, and I'm going to section it at the red line here, which is a distance y1 from the XZ plane. If I do that and draw it, I'm going to end up with a shear stress on the bottom, so multiplied by the area on the bottom, which is b times dx. That's going to give me a force, and that force has to balance these two forces on the sides from the bending stresses. Okay, and we have expressions for those bending stresses already. So if I can integrate over the area above y1, which I've labeled AY1 here, and that has to balance the force. So the force is sigma yx b times delta x, and that's going to be balancing the forces from the two sides. So at x I have the integral of mxy over I, and at x plus delta x I have m of x plus delta x y over I, and there's a minus sign here to take care of the direction of the forces appropriately. Okay, now I can go ahead and divide through by delta x, and if I do that I'm going to get an expression in the integrand that starts to look quite a bit like the derivative of m with respect to x, which we happen to know is equal to minus the shear force. So that's going to come in nicely. So let me go ahead and take the limit. If I take the limit, I'm going to get the final expression that sigma xy times b is equal to v over I times q of y1. So q of y1 is defined here. It's the first moment of the area above y1. So it's this purple area over here in the first diagram. The integral of y over that area gives me q of y1. And that gives me the shear stress on the cutting plane, sigma xy, at that location, if I divide through by b. So, and what I can take advantage of is the fact that sigma xy equals sigma yx. So we always have this symmetry of the stresses. So that then allows me to come to a final expression that is sigma xy on the cross section as a function of x and y is the shear force at that value of x times the first moment of the area above any coordinate value y divided by the width of the cross section b and divided by the moment of inertia of the cross section I. So that gives me the shear stress formula in this case here. A couple remarks. There's a quantity known as shear flow, which is sigma xy times b, so that's just a definition, and that's force per unit length along the horizontal cut in the x direction. That's a quantity that appears sometimes in analysis, and the terminology is important to know. That's known as shear flow, so that's just a definition. The other thing to sort of observe about shear is its sort of magnitude in the problem. So suppose I have a cantilever beam with a force P acting on it. And if I do that, then the maximum bending stress is going to happen at the wall here, at the top or say at the bottom of the beam. Let's just sort of think tensile. The maximum shear stress is going to happen on the neutral axis of the beam. Okay, and that so because there's this parabolic distribution of shears in the beam. And so let's compute the ratio of the maximum shear stress to the maximum bending stress in the beam. So the maximum shear stress is going to be VQ evaluated for y equals 0, B over I, and the maximum bending stress is going to be my over I. So we have the moment. The maximum value of y is h over 2, assuming a rectangular cross section, and we have I. So the i's cancel in this relationship here. And if I plug in for Q at y equals 0 is going to be a over 2, half the area, times h over 4 will be Q. And the maximum moment is P times L if the length of the beam is L. So lots of terms cancel. If I note that A is equal to B times H, I end up with 1/4 times H over L. So H over L should be a small number if I have a slender beam. And so you'll notice that the ratio of the shear to the stress is actually a small number. And anytime you have a slender beam, you'll have this dominance of the bending stresses over the shear stresses. And this is one reason why often when people think about bending and they talk about bending, they never mention the shears in the problems. But there are a number of cases where shear stresses are important, especially when you're looking at built-up beams where you say bolted different types of pieces of material together, and then the shears at those bolts tend to be important for the performance. Or also when you have beams made out of wooden materials and things like that, wood tends to be sensitive to shear stresses also, or glued sections also are sensitive to shear. So in those cases you have to worry about shear.